The first part of the presentation is on ISIDORE, Integrated Services for Infectious Disease Outbreak Research. This is a project that was launched in February 2022, and the concept behind it is that, especially after the latest example of the COVID-19 pandemic, it has become clear that Europe and the world more globally are in high need for a better capacity for preparedness and response to epidemic-prone pathogens. The fact that infectious diseases are going to emerge and become a global problem is now a tangible reality and is no more a far-fetched scenario hypothesized by scientists. So at the moment, it's not a question of if a new outbreak or epidemic is going to happen. It's rather a question of when it will happen and which pathogen is going to be involved. So in this light, Europe and the world in general need to be better prepared for future infectious disease health threats. So ISIDORE is a project that comes to answer to this need by forming a large-scale multidisciplinary consortium that is composed of 17 research infrastructures with a broad range of expertise. So ISIDORE aims to support research on epidemic and pandemic-prone pathogens, as well as the development of medical countermeasures. It's a project that has been funded by the European Commission with 21 million euros and unites 153 partners across 32 countries, offering more than 300 services. What ISIDORE offers basically is a One Health-driven portfolio of services and resources. And practically this means that you can get free access to an integrated portfolio of high-quality services. You can do this by responding to access calls for proposals that generally fall under two categories: rapid research response calls and preparedness calls. And finally, ISIDORE as a consortium internally also conducts joint research activities in order to develop new on-point services that can implement the catalog. So the access calls that are currently open are the ones you see on the screen. They fall rather under the preparedness umbrella. And in order to apply, you need to browse the ISIDORE project website, browse the catalog and identify the services that you need. You fill in a pre-application form, and subsequently you will receive an email with your ISIDORE ID number and the steps to follow in order to complete your application. The range of services that ISIDORE offers is quite wide and ranges from analytical services and structural biology to immunology, to clinical trials and social sciences and epidemiology. And it basically reflects the fact that an outbreak or an epidemic nowadays needs to be tackled at multiple levels and through different kinds of research. The added value for a researcher is the fact that you get integrated access to services and you can benefit from the expertise of ISIDORE partners to help you optimize your experimental workflow in order to best implement your project. And most importantly, public and private sector researchers are eligible to apply worldwide. So the next presentation is going to be for the European Virus Archive, which is one of the research infrastructures that that supply ISIDORE with reference material. The European Virus Archive is an EU-funded non-profit collection of plant, animal, and human viral resources offered through a network of virology laboratories worldwide through one centralized online catalog. And what is most important is that these resources are authenticated and quality controlled. They're offered through harmonized service procedures. through a consortium that has proven experience in the timely response to virus emergence and resource distribution worldwide. So this is it from my side. Thank you very much. And you can now go ahead and ask questions if you have on this first part. And next we'll follow the presentation by Christine Pratt on the European Virus Archive. Please. No. So as I don't see any questions on this first part, I will just move on to the next presentation, which is by Christine Pratt on the European Virus Archive.
So hello, everyone. It's nice to recognize some friendly names from across the world. Special hello to our friends in Singapore and in Brazil as well. I'm glad you could make it. So today I will present the European Virus Archive and how we develop and supply resources for virology research. So our mission are to collect and characterize and standardize a collection of viruses that we make available globally to scientists worldwide. So we develop and also distribute, of course, virus-derived products and non-infectious materials for use in diagnostics and research. So our ultimate aim, of course, is to facilitate access to resources and services and to support public health response during viral outbreaks. And our two next speakers, Dr. Touré and Dr. Grech, will present you more in details those different aspects. So we provide material to academia, public health, and industries as well. 30% of our end users come from industry. And we group all that in an online catalog that you can find here. So what is in our catalog? So we have viruses, of course, everything stems from viruses, but we also have derived products such as nucleic acids, antibodies, and proteins as well, and detection kits, diagnostic kits. We also have access to certain services in the catalog as well. So the underlying mechanisms for our catalog is first to be fit for purpose. So what do we mean by that? We mean that to be able to respond best to the needs in virological research, we need to cover the maximum of taxonomy. This is one of the aims that we set to ourselves. And for that, we curate all the time the catalog. We meet very regularly to prioritize what should be on the catalog and what is priority. We do have funding from the European Commission for R&D, as Semeli presented earlier. We do joint research activity to develop products that will then be put on the catalog. And from the beginning, we set a very important task on quality, and we have very detailed quality procedures. We have a harmonization of quality levels amongst all the consortium members. We also have minimal quality criteria for products to be added to the catalog. We also have a quality grading system. In terms of access procedures, we have online orders, and most importantly, we have free of charge access to some of our products. We also offer customer support. We have a unique material transfer agreement, and as we are very used to logistics in case of outbreaks, we do have procedures in place for that. And when an emerging virus is causing an outbreak, there are all sorts of questions that are arising. So what is the transmission? What are the symptoms? What are the dynamics of the epidemics? Is it a pandemic? What is the genomic sequence? All these questions. But basically, there is an urgency to gather as much information as we can on the pathogen. And in preparedness, the main objective of preparedness is to reduce the response time. And for us at EVA, it translates as those three areas. We need diagnostic kits to monitor the spread of the virus. We need therapeutics, if possible, antivirals, vaccines. We need to do research as well. And for that, we need positive controls in a matter of hours or days after the start of the pandemic. We need reference material. And we also need strains to test vaccines and antivirals. And for research, we need also genomic materials and any biotechnology tools that might be useful. So I'm going to focus on two outbreaks, recent outbreaks, COVID-19 case study, but you will hear more presented by Dr. Touré. And I've represented here in blue the different things that happened in 2020. So on the 31st of December 2019, China reported a novel coronavirus, and on the 10th of January, the genomic sequence of SARS-CoV-2 were released. And in orange, I've represented here the actions done by the EVA consortium by adding the relevant products to the catalog. So on 4 days after the genomic sequence was released, our colleagues from Charité in Berlin added to the catalog diagnostics positive control that were recommended by WHO and largely ordered. And very soon after, our colleagues added an RNA specificity panel as well, our colleagues from Erasmus Medical School. And the first SARS-CoV-2 strains were added from Pasteur Institute, from Charité, and in February, some diagnostic control that were shipped at room temperature were added by Marseille. We also very quickly added some training and sharing of know-how on the virus in various services like that. So the strength of having a network. So EVA is composed of 37 partners that act as a network. And the two main big points are expertise and response time. So here in this figure, I've represented the number of EVA orders per month in 2020 and 2021. And here I've represented the names of the EVA partners involved. So you can see that our colleagues from Germany were hugely involved at the very beginning of the pandemic, and they provided diagnostics positive control. And soon after, as I told you earlier, Aix-Marseille University developed a diagnostics kit that were shipped at room temperature and therefore allowed for a much easier shipping process across the world. And you remember that in January 2021, the first variants appeared or were characterized, and our colleagues from UK actually were the first one to distribute it. And they were soon followed by our colleagues from the Netherlands that have access to a lot of strains as well. So you remember all at the very beginning of the pandemic when there was this trilogy, you know, the COVID Tetris, you know, test, trace, isolate. That was then, you know, you would see signs in the streets about that. And in this first 3 months window, I've represented here the number of orders through EVA per week. So from the week 1 in 2020 until the week 15 in 2020. And in this short 3 months window, we distributed 300,000 diagnostic tests worldwide. And here is the total map of the 114 countries where we distributed material to in the first 9 months of the pandemic. So after the 3 months window, diagnostics companies and other companies started to add products to the market. And we saw that 32% of the companies who marketed diagnostic tests had actually ordered material from EVA. So just showing the impact that the EVA can have on the diagnostics field as well. And another example from the Zika virus outbreak, in this first 3 months window, again, 300 EVA products were distributed worldwide. Each dot corresponds to a point of a product distributed. And this is just like one example of a science paper that was published in April 2016, resolving the prior EM structure of the Zika virus using the EVA Zika virus. So we learned different lessons from those crises. The access to bioresources is key. And for that, we need field work, archiving to increase the diversity of strains available to scientists. We need a distributed infrastructure to overcome any bottlenecks. And so we need preparedness to anticipate public health and research needs. We need free of charge access to promote open science and to speed the access to our material. We have an efficient management of the IP, the intellectual property rights, with a material transfer agreement. We have quality grading, and we do communicate to our stakeholders. So how can we help? There are like more than 3,000 references on our catalog. You can check online. You place an inquiry online. As I said, there is this free of charge access program that is sponsored by the EU. And then you receive your products. And again, you can find more details at the European Virus Archive. Just a few thanks, big thank you actually to the EVA consortium that has been working together for many, many years. Each dot represents an EVA partner on the map, and we have associated partners as well, USA, Greece, Turkey, Jordan, Germany, and we are associated as well to networks such as the Pasteur Institute network and the Gabriel network from Fondation Mérieux. And that's all for me. So again, yes, if you want to ask any questions, I don't see any in the chat. Someone, yeah, a few people have raised their hands. So let me just see. No, okay. No, it was just, was it just a clap of your hands? Thank you in that case.
Yes, it was.
Okay, thank you.
So thanks a lot to Christine. And so if there are no questions at this point, we can just move on directly to Frank Toure, who is an academic researcher. And his first case study story to present. Go ahead.
It's okay. Okay, so good afternoon, good night or good morning, everyone. My name is Frank Toure from Unité des Virus Émergents in Marseille, and my talk today is called the Rapid Response to SARS-CoV-2 Viral Emergence, the Major Contribution of EVA. So, who are we? L'Unité des Virus Émergents is a French research unit created in 2008 by Professor Xavier de Lamballerie. This research unit is bringing together medical researchers and virologists. We are specialized in investigation of emergence and re-emergence episodes. Our research topics include genomics, attenuation, seroepidemiology, reverse genetics, biosafety, biobanking, and preclinical development of antivirals. So first, I would like to start, like the Dr. Pratt, with a timeline describing the SARS-CoV-2 outbreak. On the top of this timeline, you can see the main event from the first case that were described in Wuhan to the time that the WHO declared SARS-CoV-2 as a pandemic. And on the bottom, you have the history of the SARS-CoV-2 strain we obtained through EVA Global from the laboratory of Professor Christian Drosten. This strain called BAF-PAT1, which carries a D614G mutation, was isolated from one of the first outbreaks outside China. We get it really fast after its sampling around 2 weeks. With it, we developed various assays just before French went under full lockdown. And during this time, during the first lockdown, we were able to work on various topics. Most of the results presented here have been generated within the first 3 months after receiving the strain. So first, new pathogen, how to handle samples safely using chemical inactivation for molecular detection. We quickly answer this question by testing chemical inactivation with commercial buffers using SARS-CoV-2 cell culture supernatant and nasopharyngeal samples. We conducted the tests in accordance with a European standard to assess the risk of handling infectious viruses prior to RNA extraction. We quickly published methods for inactivating and safely handling samples for molecular detection. Molecular detection of the SARS-CoV-2 genome was massively used during the first year of the pandemic and was the only diagnostic tool available at this time. New pathogen, how to handle samples safely using heat inactivation. We evaluated 3 thermal inactivation protocols on SARS-CoV-2 using infected cell culture, supernatant, virus spiked human sera, and nasopharyngeal sample according to European standard. We published methods for inactivated and safely handling samples after thermal inactivation. With regard to serum handling, we found that thermal inactivation had a significant impact on neutralization titer using classical seroneutralization assay, a technique which will later become the gold standard for seroepidemiological studies and which will be massively used thereafter. Then, new pathogen, how does it behave in the environment? To answer this question, we evaluated the stability and infectivity of SARS-CoV-2 deposit on various surfaces, polystyrene, plastic, aluminum, and glass for 96 hours at 45–55% relative humidity and 19–21 Celsius degrees. We found that SARS-CoV-2 infectivity is prolonged on aluminum and glass when mixed with protein-rich media, mimicking the fomites. New pathogen, how to store and extend strains. To answer this question, we evaluated the stability and infectivity of SARS-CoV-2 following our standard lyophilization protocol and evaluated the ability of 4 common chemical stabilizers, sucrose, sorbitol, trehalose, and polyethyl glycol. We showed that sucrose used as an adjuvant represents a simple and efficient stabilizer, providing increased protection for long-term preservation and shipment of the virus under different climatic conditions. New pathogen, how to treat patients. Following its emergence, a plethora of clinical trials with repurposed drugs were launched, mostly without proper preclinical evaluation. We set up a preclinical pipeline to carry out these evaluations. This pipeline includes several in vitro assays, a primary human bronchial cell assay at the air-liquid interface, and an in vivo serial golden hamster assay linked to PK studies. We have studied a variety of molecules, mainly on demand, to document priority of or lack of priority for clinical trials. Results were used by the INRS-EMEA Molecule Prioritization Group and COVID Scientific Council to make decisions on their further use in clinical research programs. How do we find new therapeutic targets against SARS-CoV-2? To find new targets, we screen the Prestwick chemical library of more than 1,000 approved drugs in an infected cell-based assay. We then validated active compounds in a dose-response assay to obtain IC50, CC50, and selectivity index. We obtained 11 compounds, such as macrolide antibiotics, proton pump inhibitors, antiarrhythmic agent, or CNS drugs showing antiviral potency at the micromolar range. This work was preliminary, and we subsequently analyzed the most promising molecules in our preclinical pipeline in an attempt to find effective and quickly accessible therapeutics. It should be noted that this strategy of repurposing off-target drugs was not effective during the pandemic. New pathogen, how does it replicate? In collaboration with Dr. Bruno Canard groups in AFMB, we used the broad-spectrum antiviral drug favipiravir to overload the SARS-CoV-2 error connection machinery, triggering the accumulation of too many mutations and ultimately rendering the viral genome non-functional. This study provides the first detailed kinetic and mechanistic analysis of the SARS-CoV-2 polymerase enzyme. A new pathogen, how to study it. Engineering recombinant viruses is a preeminent tool for deciphering the biology of emerging viral pathogens. To generate recombinant infectious coronaviruses, we used a simple method based on infectious subgenomic amplicon, ISA technology, and were able to generate the wild-type strain, BAFPAT1, one mutant, the original one strain with the D614 original sequence, and one fluorescent virus carrying the M cherry. We then tested these different recombinant viruses for different purposes as proof of concept. The fluorescent M cherry strain for in vitro antiviral evaluation and seroneutralization assay, and the one and BAFPAT1 strains for in vivo investigation in Gundam Syrian hamster model. And finally, I would like to thank all EVA members for their hard work, all collaborators, all founders, and of course, Professor Christian Drosten and the member of his laboratory for providing the SARS-CoV-2 BAFPAT1 strain via EVA Global. Thank you.
Thank you, Frank. So there are some questions that are ongoing in the chat, but we are answering them. So yes, we can share, of course, the presentations with the participants, the presentations regarding the ISIDORe and the EVA projects. So yeah, if there are no more presentation-specific questions, we can move on to Lionel.
Good morning, good afternoon, good evening, everyone. Should I go ahead?
Yes, you can go ahead and share your screen. Share
okay.
Your
Perfect. Let me try to do that and just. Can you okay? Can you confirm you're seeing it on full presentation mode?
Yes, perfect.
Okay. Okay. So hi everyone, and thank you. Really, I want to thank the organizers for giving us the opportunity to share a bit our experience at PAHO with the use of EVA reference material, which has really been key in many instances in our efforts of better preparing laboratories in the Americas and responding to outbreaks of emerging and re-emerging material. Before I share with you some of these examples of use of the EVA material, just want to quickly mention who we are for those who might not know us. So I work at the Pan American Health Organization within the Health Emergencies Department. This is a public health emergencies a public health agency that was created in 1902, and that kind of wears two institutional hats. It's since 1902 it is the specialized health agency of the Inter-American system, so all countries of the Americas, and since WHO was created, it also serves as the regional office for the Americas of the World Health Organization. And our mission really is to lead collaborative efforts among member states and also other partners to promote equity in health, combat disease, and improve the quality of and lengthen the lives of the peoples of the Americas. Our membership is 35 member states, so all independent countries in the Americas, and we also have participating associated and observer states that might have different political statuses. So the first example I want to share with you, and it is the first time we collaborated with EVA on a response to a public health emergency. It's the example of the yellow fever outbreaks that occur in Brazil between the end of 2016 and the end of 2018. And yellow fever is endemic in Brazil. It's actually endemic in certain countries and territories in the Americas. So seeing yellow fever is not unusual. And this is the numbers of reported cases in maroon and in blue, and the reported deaths per year in Brazil since we actually collect data, so since 1960. And you can see that for a period of 55 years, we detected regular cases of yellow fever, unfortunately linked to some deaths, but and some with some epidemic years, but the number of yearly cases was maybe around 20 of detected cases, 25 cases per year, and a handful of deaths. And at the end of 2016, actually in December of 2016, we started seeing an increase in the number of cases. And actually in 2017, we had as many cases in that single 2017 years than in the period from 1980 to 2016. So in a period of 35 years. So 2017, we had over 800 cases and close to 300 deaths, and we had almost double the amount of cases in 2018, with over 1,300 cases and more than 400 deaths. And then that number declined, and we are now back to a kind of a normal situation. And what we also observed, it was a shift in the circulation of the virus. So in the Americas, the virus is transmitted from non-human primates to humans via mosquito. There hasn't been any human-to-human transmission via a mosquito in a long time. And what we started seeing in 2016, it was a shift, movement of the virus, of the cases. These are human cases detected in the 2016-2017 season in yellow, 2017-18 in orange, and then 18-19 in red. And you can see that we, in 2016-2017, the first year of intense circulation, had a lot of cases in this southeastern region of Brazil. This is the state of Minas Gerais, and then a shift to the state of Espírito Santo, and then to the states of Sao Paulo and Rio de Janeiro. And one of the main concerns here was that these areas, especially these coastal areas, were not considered endemic areas of yellow fever. So the vaccination in these areas of Brazil was not recommended or mandatory. And we were dealing with large populations. So the two cities of Sao Paulo and Rio in particular, that were vastly unvaccinated. So so what was the main, or one of the problems we were facing then at that point? It was that there was a need really to expand the RT-PCR detection capacity of yellow fever virus from the national labs, where it was mostly centralized, to public health state labs. So every state in Brazil has its own public health laboratory, and the idea was that we wanted to bring that RT-PCR capacity at state level to really support timely identification of cases, and then also expanding RT-PCR versus other tools like ELISA and serology, because we needed specific identification. And for reasons I'm not gonna expand on right now, detection of yellow fever and other viruses of the same family by serology might be complicated to have a specific detection. So using RT-PCR was really key. So this was one aspect of the needs, and the other aspect was more in terms of preparedness, preparing neighboring countries which were endemic for yellow fever, or even non-endemic countries, to implement that diagnostic capacity, thinking of for non-endemic countries of the possibility of having imported cases. So what was our response? So did a lot of work on updating the laboratory recommendations, laboratory algorithms, emphasizing the importance of using molecular RT-PCR testing. We deployed teams of virologists to conduct the trainings in the states labs in Brazil, and also in national labs. And we supported these laboratories as well with the specific procuring RT-PCR reagents. But of course, to be able to do that, we needed reference material, and with the support of one of the partners of EVA, which is the Robert Koch Institute, in this case, the group of Dr. Cristina Domingo, we had access to yellow fever virus positive controls. We actually made 2 large requests in 2017 and 2018, and these controls were distributed to over 40 laboratories in 26 countries, included that the network I was mentioning of public state public health lab in Brazil. And we also distributed through EVA and distributed then Zika virus controls that serve for differential diagnosis. And I think one interesting thing to point out here is that beyond that work on accessing these reagents that enable the implementation of RT-PCR for yellow fever in many public health laboratories in the region, we continue collaborating with the group of Dr. Domingo, and we actually organized in 2018 in collaboration with her group an external quality assessment program for yellow fever virus RT-PCR, which I'm not gonna describe in details, but was basically distributing a panel of 15 samples to enable testing for the sensitivity and the spectrum for yellow fever detection. There are different genotypes or strains that you want to make sure that you are detecting, and also, of course, for specificity. So, and this is just this panel was distributed to 32 laboratories in 23 countries in Latin America and the Caribbean. And the second example I want to mention, of course, is COVID-19, as many of the colleagues have spoken before me have done already. So you'll see the same or a similar timeline with the December 31st, 2019, the alert, and then the isolation of the coronavirus announcement and the release of the sequences, and the availability on January the 14th of the first RT-PCR, or at least publicly available RT-PCR protocol, which was posted on WHO's webpage. And at that time, we, of course, in January, so this mid-January was around the time we at PAHO activated our response system, our incident management system for COVID. And it was also the time where we started researching and acquiring RT-PCR reagents for that virus. So we started getting for many sources, kits, primers, probes, controls, and started distribution to countries in the Americas at the end of January, and then started a series of trainings to enable laboratories, national laboratories in this case, to conduct testing. And we had 9 in-country missions where our team went to support the implementation, and then 2 sub-regional networks in Brazil and Mexico where we supported training for 18 countries. So in that manner, and here you have the details of the trainings and countries visited in a period of 4 weeks from January 27th to February 24th. We had basically the 28 countries in Latin America and the Caribbean, which were trained on the SARS-CoV-2 RT-PCR and who had access to reference material. And this was basically all countries that had PCR molecular capacity. So there were few countries that were not trained at that time, but that was because of a lack of laboratory infrastructure, and those were trained in the following months once the infrastructure was built. So here the support from EVA is a bit similar to the example I was showing from yellow fever, but at a different scale, of course. So here our public health need was to implement a reference molecular protocol for SARS-CoV-2 before the introduction of the virus in the Americas, so that countries are prepared to detect the first cases and then to track the spread of the virus. In terms of response, we also published our laboratory guidance on this new virus, conducted the trainings, as I mentioned in the previous slide, and acquired and distributed RT-PCR reagents. And here, as was mentioned in the previous presentation, we had the chance to collaborate with Felix Drexler from Charité Hospital in Berlin, and that's through EVA where we got our first batch of controls. In this case, it was for one of the 2 assays they had developed, the e-gene assay. And just want to mention again that this was all very timely, very quick. We requested the controls on the 20th of January, got free of access charge 1 day later, and in a bit over than a week, the controls were shipped from Charité to our headquarters in Washington, DC, and from there we distributed them to the labs. And then we ordered different batches of controls for another specific assay that was developed by the Charité group, and also ordered full-length RNA controls to support standardization of countries that had implemented other RT-PCR assays. And in total, these controls were distributed to 36 countries and territories, and also to CARPHA, which is the Caribbean Public Health Agency, and that serves many small island developing states or territories in the Caribbean. And this initial contact with the group in Charité through EVA, enabled by EVA, also allowed us to engage in a further collaboration with the group, and in particular at those early times of the pandemic, of sharing critical information on the temporal dynamics of the RNA that was detected by RT-PCR, and also the use and processing of other sample types like sputum, saliva, etc. So I think with these 2 examples, I think really highlight how the EVA reference reagents have been key in our laboratory preparedness and response efforts in the Americas through several epidemics. I mentioned yellow fever, Zika as also as part of the yellow fever response, but that also, of course, was useful also by itself, as it was mentioned Christine's presentation, Mpox, which I didn't mention, but where we also, through a similar process, trained and distributed reagents for many countries in the Americas to enable PCR detection, and of course the COVID-19 pandemic. And I think what's important for us now is that this this collaboration with EVA is now in place, and it's really important to strengthen our laboratory networks and to tackle any endemic or newly emerging diseases. And as I tried to outline in the two examples, there are opportunities that emerge from this accessing these reagents in terms of exchanging scientific information and collaboration. And I think that the next step might be really to think of further avenues for collaboration, and one of those could be EQAs for some of the diagnostics and reference material that are distributed through EVA-G. So before I close, just want to thank all the institutions I've mentioned. Of course, the coordinating team at EVA-G, the group of Cristina, Domingo, and Robert Korsch, the group of Felix Drexler at Charité, University of Ljubljana, where we got our Mpox and monkeypox virus reference material, and our laboratory response team at PAHO headquarters, and all of you for your participation today. Over to you, Semeli.
Oh, thank you, Lionel, and thank you, Frank, as well, for these very nice presentations. I think it's really quite good examples of how the tools available provided through the European Virus Archive can be used. And I would just like to make the point that, as all of you know, but I think it's never it's always worth stressing more, that response cannot exist without preparedness, and preparedness cannot exist without research. So I think that as researchers, it's very useful to know what tools are available. So I would just invite all of you to go ahead and explore the ISIDORe website, the European Virus Archive website, and just become aware, if you're not already, on what options you have to help your research. So yeah, I don't see any more questions or comments. So I think that we are spot on for time, and thank you all for having participated. Thanks again to the external speakers, and of course to Christine, Pratt, and yeah, we can end this webinar now. Bye-bye.
Thank you very much.
Bye, see you.
Thank you, goodbye.
Where should I be? You can have something to do.